Conceptual design and analysis of dome for underwater application. There will be an enormous increase in pressure as we go to ocean depths. External pressure from the surrounding is exerted on the underwater vehicles. For an underwater vehicle, the dome shields the hardware and is subjected to tremendous pressure at one time during operation. As a result, the dome must be qualified for the pressure. Dome models are developed based on mechanism, materials, and geometric constraints. SolidWorks is proposed for the design, modeling and drawing generation of the dome. ANSYS Workbench, the finite element software to carry out the analysis. Considering stress criterion for design and analysis is carried out by the effect of changing the material type, properties, and eventually the best dome is suggested. Suitable evaluating methodology is suggested. Keywords: dome, pressure, factor of safety, von Mises stress. 1. Introduction. Underwater bodies. Vehicles or missiles that are operated underwater are called underwater bodies. These include submarines, torpedoes. These vehicles are subjected to an enormous external pressure from the surrounding water. During emergency conditions, these vehicles dive 300-450 m deep from the water level, resulting in increasing pressure. Water has high density in which it exerts high resistance to the movement of the body. Dome. Dome is the component of the vehicle that protects the hardware which acts as nose cap to the underwater vehicle. This dome shape can withstand the pressure required. As a result, a dome shape must be created with desired material. There are different sorts of heads, with the hemispherical head being the best fit for our needs. Before a structure is used, it should be studied experimentally. See hemispherical dome, or heads. The head depth is half the diameter of these heads, which has a radial geometry. 2 pressure heads are arranged back to back in these storage heads, forming a storage sphere that efficiently stores materials under high pressure. Hemispherical heads are thinner than shell heads and have a standard code 3:1 that taper during the transition. Hemispherical heads are usually made from welded sheets rather than the flat sheets used in the other head varieties. This makes it the thinnest head on the market, as well as one of the most expensive. These heads are ideal for applications that need high-pressure storage or vessels with enormous diameters. Figure 1 hemispherical dome with 7 mm thickness modeled using SolidWorks. To complete the structural qualification, the specimen should be tested in the actual environment. During testing, the test specimen must be able to withstand all forces exerted on it. Because the dome has such a significant impact on the total body, a specific design is created using various materials. There is 1 bar increase in pressure for every 10 m of depth. At one point during its operation, the dome of an underwater vehicle is subjected to a pressure of 25-40 bar. As a result, qualification of this dome for the pressure is required. Hence dome is designed to take up the pressure of 30 bar. 2. Valuation for initial thickness. Materials properties. Product standards define the limits for composition, quality, and performance, and these limits are used or presumed by structural designers. Aluminium 6061 alloy is originally called as ALLOY61S. It is a precipitation-hardened alloy and the most commonly available and heat-treatable alloy. It has a density of 2.7 G/cm3, Poisson's ratio of 0.33, and a shear modulus of 26 GPa. It also having a good value of Young's modulus, which is about 68 GPa. AL6061 alloy can be easily formed and has excelled weldability. It is also having a minimum yield strength of 276 MPa and tensile strength of 310 MPa. Titanium grade 2 is another material which is lightweight and exceptionally corrosion resistant. It has. Model is imported into ANSYS Workbench. In static structural analysis, material is assigned as structural steel and meshing size as fine. Fixed support is applied along the base of the flange and internal pressure applied is 30 bar. Solution is derived for total displacement, von Mises stress, equivalent stress, and equivalent strain. The values thus obtained are as follow. To validate any design, it must satisfy minimum FOS of 2.5. Equivalent stress is found to be 126.13 MPa, which derives FOS of 1.982, which cannot be validated. Hence multiple iterations are carried out to meet safety factor of 2.5. Modeling and analysis are repeated for new iterated thickness. The respective values are stated in tables. 5. Conclusion. Based on input values 30 bar pressure, 2500 mm and 3000 mm outer diameter, and aluminium 6061, titanium as materials, dome thickness is calculated using pressure vessels concept. Using this thickness value, modeling is carried out using SolidWorks and analysis is carried out using ANSYS Workbench. Hemispheric dome requires the least amount of material and has the smallest surface area to cover a specific volume and cost efficient too. In aluminium dome model of outer diameter 3000 mm and 9 mm thickness, the value of FOS is 1.96, which cannot be validated. Iterations of this design with outer diameter 2500 mm and 7 mm thickness is designed and modeled. Analysis is carried out. It was observed that this dome design has the FOS value 2.64, which satisfies the minimum required criteria. Similarly, in titanium dome model of outer diameter 3000 mm and 7 mm thickness, the value of FOS is 2.1, which cannot be validated. Iterations of this design with outer diameter 2500 mm and 6 mm thickness design is modeled and analysis is carried out. It was observed that this dome design has FOS value 2.3, which does not satisfy the minimum required criteria. From the above 4 cases, it is observed that aluminium 6061 material with 7 mm thickness has required factor safety and can withstand the pressure applied on it. This dome can protect the hardware of the underwater vehicle. It is also observed that this designed model has less mass of 187.4 kg and cost efficient. 6. Future work. The characteristics of a material are mostly determined by the load acting on the surface, the type of environment in which it is being operated. Clearly, the analysis shows that aluminium 6061 with a 7 mm thickness outperforms titanium grade in terms of characteristic qualities. A proposed composite alloy containing titanium alloy 6%, aluminium 4%, and vanadium is being investigated, with tensile strengths of 1000 to 1100 MPa and useful creep resistance of up to 300*C of about 570 MPa for 0 to 1% total plastic strain in 100 hours. It would be extremely resistant to fatigue and crack propagation. This composite material might help the engineers to manufacture the dome with high corrosion resistance and withstand all the loads, and also plays a key role in protection of the hardware of the underwater vehicle. This designed dome with various thicknesses can also be used in the construction of sturdy fuel tanks for use in rockets under specific heat conditions. This dome designed with high standard materials and high withstanding capacity can control the fuel pressure in it without any failure. 7. Acknowledgement. We extend our thanks and gratitude to our scientists, Mr. R. Gopi Krishna, Doctor of Science, DRDL Hyderabad, for his invaluable guidance for helping our project. We would like to convey our sincere thanks to them for their consistent noble guidance, continuous support, and valuable suggestions which inspired us to make this report fruitful. There are many more who cannot be forgotten, and we wholeheartedly thank each and every one who graciously helped us directly when we were in need.